All right. Last time we talked about one form of graph, two forms actually. We talked about a histogram, and we talked about a frequency distribution line graph. What does the histogram look like? We can't say it because there's another graph called a bar chart, but there's a difference between them. A histogram, all these bars touch each other. The frequency distribution line graph is you start off at the origin and then you go to the data points and you put straight lines. Now we're going to look at some other ones. The next one we're going to talk about are called dot plot. With a dot plot, what you do with your data there, you only have a horizontal line. The data, let's say it's 20, 30, 40, 50, and 60. All you do there is when you look at your data, if it's a 20, you put a mark there. If it's a 25, put a mark there. If you get another 20, a 40. So you put little marks and you go up the bar chart there, up the column there. That is a dot plot because you put dots above the graphs where they are. Any problem with that one? Yes. Well, okay, let me make up a data set so we can look at this. I have a data set, but the numbers are way too big. So here's our data set. I'll use numbers from 0 to 9. So I got 1, 5, 7, 7, 3, 4, 2, 1, 7, 9, 8, 0, 1, 1, 7, 2, 5, 6, 1, 7. That's my data set. So the dot plot, since we know our data is between 0 and 9, we'd have on this line, we have our integers, our outcomes, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Those are all possible outcomes. So above there, we look at our data set. Any number we see, we just put a dot above that corresponding number. So at 1, because if there's no dots, what's the value of it? 0. So we have 1 dot there. Then we go to 5, put a dot above there. We have 2 for 7, and they just stack on top of each other. 3, 4, 2, 1, 7, 9, 8, 0, 1, 1, 7, 2, 5, 6, 1, 7. So that's how a dot plot works. What is it good for? It shows you pattern. All graphs are meant to display the behavior of the data. So what can you tell me about that data? by looking at it. Whatever 1 and 7 are the most popular, or the most frequently occurring. And if we think about this, we can create a frequency chart. Here are our outcomes. Our outcomes are possible from 0 to 9. And the frequencies, so how many zeros do we have? How many ones? 5. Number, how many twos? And there's 1, 1, 2 5s, 1 6. How many 7s? 5, 1, and 1. So yeah, so we take our frequency chart, we can now move it over to a dot plot. Or we just use a dot plot. The difference is, what can we do with a frequency chart? Can we do anything else further beyond that? Well, yeah, remember yesterday we did what after a frequency chart? We found a relative frequency, which is the percentages of each one of those. We can't do that with this. All we could do is we could find the relative frequency and say that because there's 20 numbers and there's 5 there, this is 25% of the data. This is 25% of the data. Okay, so that's what we're looking at there. So again, the choice of graphs that you use for your analysis is very important because it's supposed to help make it easier to interpret what the data is saying. The next one is called a stem plot. The stem plot is made up of 2 parts. Yes.
For the dot plot, do we need to find the cumulative frequency?
No, you can't, because there's no column for it. It's just a straight up picture, nothing more. Now, the reason they call this a stem plot, because you look at a flower or a branch, you have the stem, you have flower on top, and then you have a leaf that comes off that. That's how this works. So let's say our data set looked like this. Um, 3, 15, 22, 7, 19, 11, 25, 40, 42, 30, 35, 33, 11, 2, and 10. Let's say this is our data set. Here, we have the stem part that goes here and the leaf part that goes here. The stem part is the farthest left digit. The leaf part is the one, anything after that. So what we're saying here is our stems. Since we have a 1-digit number, the number 3 can be written as 03. So we can have a 0, 1, 2, 3, and 4. Because we have no other data that's higher than 4. The first digit is no higher than 4. So all we do now is we look at, for the stem of 0, how many 1-digit numbers are there? And we put that number in there. So we put a 3, a 7, and a 2. How about all the numbers that start with 1? We have a 15. We have an 11. We have a 19. We have another 11. So you see the tens numbers go here and the ones digit goes here. We have a 22, 25. Let's look at the 30s. We have a 30, 35, 33. Oh, we have a 10 also. I forgot that one. And then we have a 40 and a 42. Okay, so if you see this, this is similar to the dot plot, but it's turned sideways. Yeah, because the dot plot, the baseline is horizontal and everything grows up from there. On a stem leaf, the line is vertical and we go horizontally out. So yeah, it's just a rotated graph. The difference is here in the first example I gave you, all the numbers were either 20 or 30 or 40. It was even, but what if we had numbers in between there, like 43, 41, 28? We would have a lot of data in there. But with this, with the stem leaf, you can tell me what number is this? It's a 25. This one here, it's in the one, so it's 1, so it's 11. So that's how you read a stem leaf plot. So far, so good. What you normally do also is in each one of your sets, you would put them in increasing order. So this one would actually look like here's 0. We'd have 2, 3, 7. On the ones row, we'll have 0, 1, 1, 5, 9. On the 2, we'll have 2 and 5. 0, 3, 5. And 0, 2. We're going to find out why this is important. We'll start doing more calculations, because once you have a data set, is the data set in any specific order? No, it's in just how it's as you collected them. What you normally have to do is set your data in an increasing order, and then from there we can see what things we're looking for, and those will become more apparent in the next couple of chapters. And this also, we can, when we do this, we've taken this entire list and put them in order. Because now, if we take this list and follow the stem plot, we have 2, 3, 7, 10, 11, 11, 15, 19, 22, 25. So you see, I've now been able, with the stem leaf, put them in increasing order. And we kind of looked at something like this last time. The time series graph. The first two, the dot plot and the stem leaf, the data is just the values, not when you got them or where you got them. You can't do anything else. But if your data is time specific, or if you're observing something throughout the day, you want to look at each hour, you want to see what happens. That's what we're saying. It's a time series. or if you're looking at something over days, weeks, years, months, you have the vertical axis and the horizontal axis, the regular graph. Time is always on the horizontal axis. Always. For anything you do, time is always on your horizontal axis. And whatever outcomes you're looking at are on the vertical axis. So let's look at 10, 20, 30, 40, 50, 60, 70. In the year 2000, 2001, 2002, 2003, 2004. Let's pretend we're looking at the number of homes that were built in an area. We're looking at by year. So in the year 2000, let's say that 20 homes were built in this district. Then 2001, it jumped to 60. In 2002, we go down to 50, and then stay at 50 in 2003. And then 2004, we drop down to 30. So it's kind of like a line because we connect each one of those data dots with straight lines. So, and each year you have whatever whatever time period you have, whatever you're observing. What good is something like that? When would you use a time series graph? Exactly. Yeah, and that's what you do because in the medical field, your time again, time never. That's the reason your horizontal axis is always time because it never goes backwards and it never stops. So if you're looking at your patient, you can look at the date like 9/1 at 8 o'clock, 9/2 at 8 o'clock. So you can look at each day, or you can look at during the day, how many times you do this sequence, your pulse rate. So yes, medical is very, very, very time sensitive. Yes, actually, yeah, they do that is to see how early should we open up early enrollment. How many of y'all ever early enroll when it first opens up? Yeah, if you want to take a specific class or specific teacher, yes, you have to. Because if you wait to the last minute, the class and the teacher may be gone. All of us have been through that. So we learned, yeah, if we want something specific, then we'll register as soon as it opens. But if you don't care, if all of them are the same, then you can wait whenever you want to. And that's what they do. They see okay, when, and then not only that, they see what kind of classes fill up faster. They want that because the classes that fill up faster need more sections because there's a large interest in them. All right. The next one is unlike the histogram, okay, where we had each of our data touching the sides touching each other. A bar graph each bar represents its own data. The histogram and bar graphs, they represent what? Frequencies. So with the bar chart, or the bar graph and the histogram, although they look the same, they represent the data separate differently because the histogram, the sides have to be connected. The histogram, like we did yesterday, we can look at an interval of data. Histograms are great at looking at intervals of data. Bar graphs are good for usually single discrete numbers. Another thing, the width of your bar charts, your bars all have to be the same width. Because that way, if you saw a graph that looked like this, subconsciously you would think that these data values are not the same, or they don't carry the same weight. Or if it was like this even. So to get that away, even though that it's the frequency, it's only how high it goes, it's what's important. That's why you want them all to be the same width. So there's no other ambiguity about it. The next one you probably have never seen before. It's a Pareto chart, or a Pareto graph, I should say. A Pareto graph takes the histogram or the bar chart, you do either way, and makes it in decreasing order. So let's look at this example. We'll use these numbers here. So the biggest was 4. Then we had 6 and 8. They both had 7. And then 2 only had 5. That's how a Pareto chart is situated. It starts with the highest and goes down. Why would you do that? How do you read a chart? Left to right, like you read everything else. So if this is a report and you see this, you want to know what's the most important one first, the most frequently occurring one. Typically, a Pareto chart is accompanied by a cumulative frequency line graph or frequency distribution. Cumulative line graph. In other words, what happens on this overlapped on the same graph, what you're going to see is you'll see a graph that mirrors 100% of the data. So from here, it went up 8, then it went up 7, went up 7 more, then it went up 5. The reason they do that is to tell you that this data represents 100% of all your data that you have. Because if you're missing any data on your graph, you have to tell me that. And what I'm going to do is just skip over that graph because it means nothing now. So this is a cumulative frequency distribution, or the line graph. Remember the the plane crash one? We had plane crashes. We had our frequency distribution. The cause and the frequency. Pilot error was 640. Mechanical was 195. Sabotage was 95. Weather was 63. And anything else like act of God, which you call forced majeure, like an animal or a volcano or something like that, earthquake. So on the horizontal, we put the causes. So we have pilot error. And it goes up to 640. The next one is mechanical, and it's only 195. After that is sabotage, weather, and then other. Now, the reason you would leave it like that, because normally the other would be between your mechanical and sabotage because it's decreasing, but because mechanical is made up of so many other things, it's bird strike, it's drone accidents or other collision with other airplanes. It could be so many other things. That's how come we have the other split up by itself at the very end. If it's a unique issue like pilot error, mechanical, sabotage, weather, they have their own columns. And since other is made up of so many other things, we can't go any further. What kind of graph is that? Was that Pareto? Yes. Very good. Pareto chart. The next chart. You are probably familiar with these. The pie chart. The difficult aspect about a pie chart is how you create it. To create a pie chart. Well, first off, what does a pie chart look like? Yeah, like a pie. It's round. And then each of those items are made up by different size slices. So we say something here, it's pilot error. And we have to determine the percentage of that circle. And then we have mechanical. It's made up of a certain amount of percent. And then these other ones. But that's not the hard part. Let's go back to look at our data for the here we have our cause, the frequency, pilot error is 640. Mechanical is 195. Sabotage is 95. Weather and other. Because in order to find the percentage of this circle, we have to find a relative frequency value. Remember how we find relative frequencies? The relative frequency is equal to what? The frequency of that element, the total number n times 100. Very good. So the first thing we have to, pardon? The class would be pilot, air, mechanical. Those would be the classes. Those are your horizontal lines. Well, the elements would be, yeah, 640, the frequency number of those elements, right? And then n would be the summation of all those frequencies. So what do we have here? We have 640. 1104. That's n. So our relative frequency for 640, we did those yesterday, didn't we? So what's the percentage for the pilot air? 58%, 10%, and then we have to always add those percentages up. Because what should it equal? Should equal 100%. If not, then you're missing some data. But again, because we rounded these up to begin with, we'll have round off error. So what does it equal? We have 68, 78, 87, 93.
The second one is 18%, not 10%.
What is it?
18.
18, okay. Well, that makes it 5, 6, 7, 8, 6, 9, 2. All right. All right, so we first find the percent. Now we got to find the degree. Because a circle has how many degrees? 360 degrees. So what is 58% of 360 degrees? So we take 0.58 times 360. Point 0.58. Yeah, 208.8 degrees. Or we can make it, because it's gonna be tough for us to do decimals, we would round it up to 209. So what we would do, we'd start at one point. We'd have to have a compass if we do it by hand. We know 90 degrees is this, 180 is down here. So it's roughly about that much. Because from here to here is roughly about 208 degrees. Because 180 is straight down to a couple more. Then how much is mechanical error? 18% of 360. 55? 65. Okay, so from this line, we would cover 65 degrees. So from here to here is 65 degrees. .09 times 360. So 33%. That's 33 degrees, I mean. 6%. So from here, we'd go 22 degrees. And then 10% would be 36 degrees. Yes, a lot of teachers will teach you, okay, let the computer do all the work. But the problem with that is, how do you know that the numbers they give you are correct? You always have to test the values first. So by taking a small bit of data, doing this and seeing if your graph works the same as theirs. Because I can tell you right now that the formulas that are used, there are usually multiple different types of formulas depending on the size of data and how you collected it. The formulas change. So this is what your graph would look like. So we know that 58% is pilot error. 65%, 18%, which is 65 degrees, is mechanical. This is 18%. This is 58%. And so on and so forth. So that's why the pie chart is used a lot, but it's very difficult because you have to make sure you convert it from your data to a degree representation of that data.
Was the total of the degree has to be 360?
Yes, because yes, it should be 360. Yes, that's going to be because of round off error. And again, now if we use a decimal equivalents of these numbers, then we have it all. We're going to have some error also, because where do we end the decimal places? Do we end it at 1 decimal place, 5 decimal places? The more decimal places you use, the more accurate, but the more difficult it is to actually graph it yourself. And that's why people use calculators, computers to do this. But you have to understand how to do it yourself. So that's the pie chart. The next one is the frequency polygon. We've done this one already. Because the frequency polygon is the line chart, where you put dots everywhere. It's the line chart. It always starts from the origin and goes from there, or whatever your zero value is. And these are the class frequencies. What do I mean by class frequencies? 640 is the class frequency of pilot error. 95 is the class frequency of sabotage. So it's just a way of saying the frequency, the number that corresponds to it. The beautiful thing about actually a lot of these, the limitations are, can we compare two or more informations with that same graph? Can we use a histogram to compare two or more? Yeah, what you can say there is this is everything for outcome A. Then everything for outcome B. It doesn't look good, but you could do it. And the way you do it, you make each of these have different colors. Instead of using the histogram, what we would use there would be bar charts. So this is outcome A, this is outcome B. Have you ever heard of a stacked bar chart? I'm not crazy about it, but it's used. What it is, let's pretend this is 3, this is 5, and this is 1. A stacked bar chart would be for A, I would go 3 would be the first one, 5 would be the next one, and 1 would be the last one. So all of these are whatever A is, but the length of them tells you how much you have, and they have the number inside of them. Makes you have to think more, which I'm not too crazy about it, but it saves space. And these are usually different colors. So the first, whatever the first outcome is, that's red and blue and yellow, whatever you want to. But these are different ways you can do them. Can you do them with pie charts? Can you compare two or different on the same pie chart? No. It's like mixing a chocolate pie with a pumpkin pie. It'll taste good, but it wouldn't be, you couldn't tell two different pies. It would be its own unit. So no, you can't. Frequency polygons, we can do that. We can put multiples. So like one of them, on one of the data set, we'll make all the points with circles. The next one, we make them with X's. So we would connect the X's. Then the next one, we'd have boxes. So that way you can follow along with different ones. So with the frequency, typically the frequency polygons, that chart is what's most, if you're going to compare two or more pieces of information, use the frequency polygon. Because it'll make it much easier to follow along all the boxes, all the circles, all the X's. And the beautiful thing about it is it's not going to, the bar chart or the histogram or the stacked bar, it's not going to take up that much space. So far, so good. Another one you probably have seen, and actually I know you have, because if you took the SAT or any type of standard exam, you have one of these. Pictograph. Pictographs are actually, they use pictures to represent amount. One way of doing a pictograph is, let's say we're talking about what's easy to draw? Cars. Each car represents 100. So in May, we see this. In June, we see this. And in May, you had 3 full pictures of cars. Remember, each car counts as 100. In June, we have this. In July, since it's only a partial month. So what these do is these pictorially represent not accurate numbers. Because if each car, full picture of a car represents 100 cars, how would I represent 90 or 60 or 20? So when you use something like this, a half a car would be how much? So yeah, so this is 100, this is 50, so we had a total of 150 sales. In May, we had 3 full cars, so that's 300 sales. And July so far, we only had 50 sales. So that's one way you could do it. Another way is, well, actually, by showing a size. If I had a picture of a tire, a wheel, and then I showed you this picture of a wheel, it looks about twice the size, doesn't it? So if you saw this, they're saying that if this is in May and this is July, you can say that our sales of tires has doubled. But obviously you can see the problem with that. It's just guesstimation what you think it looks like. And here's even more important thing. When you expand things, for example, when you expand a 2-dimension object, like a square, as opposed to a cube, if you double these, so if the area of this one, if the area of this one was 4, if we double it, what happens to the size? It doubles. So what's our area now? If area is 4 here, what would this one be if we double it? It would say 8. But let's look at that. When we double it, each side doubles. So instead of 2, they become 4. Now what's the area? 4 times 4 is 16. So you can't just double the area. We double the area, that means you're doubling the lengths of the sides. This one from 2 to 4, so 4 to 4 is 16. How about volume? If each of these were 2 units, what's the volume of this one? 2 times 2 times 2 is 8. If we double it, do we get 16? No, because now we get 4 times 4 times 4, which is 64. Be very careful about when you say, I have this and I double it. It's not the volume or it's not the area that doubles. It's the object itself that doubles. So that's why picture graphs are a lot of times bad to see. Actually, and in your picture, in your last page, example 9, I gave you that picture right there. So in year 1, 151 million phones were collected. They're back there. Yeah, whenever you get here, always check the back tables because that's where I put all the stuff. As opposed to year 2, 534 million phones were collected. We're on section 3, chapter 2, section 3. All right. Make sure if you have a single sheet, it's wrong because it has to be stable. Remember the problem we had yesterday about the stapling? It's always the top sheet doesn't get stapled. So if you have a simple sheet, make sure you get the stack behind it. Yes. We're looking for this stack here. It says chapter 2, section 3.
We have it, but the last one is not there. The last page you're giving us now is not there.
Turn it over. What is going on with these printouts?
The one on the app.
It's on that one.
Yes.
Yeah, exactly. That's the same thing I do there. I send it to. So you did receive it via. Okay, yeah. So yes, you should have gotten all my stuff from yesterday. Yeah, make sure that you re-register for this course in summer 2 on Remind. Don't carry forward that. So what it says here, the problem with this is, does this phone look twice as big, 3 times as big, 4 times, or 3.5? If we look at the numbers, 151 as opposed to 534, it's 3.5 times bigger. So again, pictographs are only use them for simple things. And if you have something like this, don't believe it because you can't really measure how big it really is. Yeah, and in our tech center on the very bottom, you guys don't have the last page. Online, you'll have these. So actually, I'm gonna just stop printing them out because I don't know why that printer is not working. I'm just gonna send them to y'all because that printer is not working for whatever reason. I apologize. I cannot apologize enough. Okay, I'm not gonna subject it. I don't know what's wrong with that thing. But anyway, if you have a TI calculator, you have access to histograms, time series, frequency polygons, and scatter plots. If you use Excel, you have histograms, time series, bar charts, Pareto charts, pie charts, and scatter plots. So out of these, again, that's what I'm saying, is use Excel. It's free. It's on everybody's computers. And also, as students, you guys get some free software, don't you? So make sure you check on the website and see what free software you get. Microsoft Office, the entire suite, Adobe, and all that sort of stuff. You get free access to those. All right. So that's it for that section. That has to do with this contract. Oh, actually, no. Let's look at this. Boom. Here's an example. This is going to frustrate you, I think. But I just saw it this morning, so I thought it was interesting. Let's go ahead and use this one. So what this thing says is this. Let me read it to you. An insurance company determines vehicle insurance premiums. What are insurance premiums? It's a month, your monthly payment just to have insurance for your car. It's based on a lot of factors. It's based on your age, your race, your gender, your education background, the type of car you drive, how far you drive, where you live, where you work. All these factors are taken into consideration to determine your premiums. They're based on known risk factors, which I gave you all those. If a person is considered a higher risk, you notice they don't tell you who's at higher risk. So what kind of people do you think are at higher risk? Men or women? Yes, you'd think, but that's what they think too, because of the machismo effect. But in reality, more accidents occur with women. Because not only, how many times have you ever seen anybody, or yourselves, ladies, I'm not to be generalizing, but have you ever done makeup in the car while you're driving? I'll never forget. One time I was driving to an event in Dallas, and the car next to me, the lady not only had cell phone in one hand, she was putting on makeup with the other one, driving with her knee on the highway. So again, I'm not generalizing, but it's scary. If a person is a higher risk, their insurance premiums will be higher. One potential factor is the color of your car. The insurance company believes that people with some color of cars are more likely to be involved in accidents. So can you take a guess on which color is the most frequently occurred? Because red is an aggressive color. Blood. You always picture them of the red Ferrari, the cherry red Mustang. So yes, and that's why police always look for red cars on the highway to see if they're speeding. How many of y'all have red cars? Why did you pick a red car? No, I agree. Yes, but yeah, it's a lot of times it's a subconscious factor saying that looks pretty bad. I like it. I am a firm believer. White is the best kind of color car to get, especially in Texas, because it's not going to get you're not going to get so hot inside there. Black is the worst kind because that sucks up the heat. It makes you have to use more air conditioning. So yeah, it's besides all this other stuff. It's just the ecological aspect of it. So to research this, the insurance company examined police reports for recent total loss collisions. Here's the data. The color blue, there's 25. Color green, 52. Color red's 41. Color white, 36. Black, 39, 23. So are we right about our hypothesis? We said that red is the most frequently occurring. According to this, it's green. But now well, we have to, if you read this, actually, I probably left it off, but it all depends on where the data was collected. It's from the police office, but what municipality? Is it a rural? Is it a country? Is it urban, suburban? Or is it city? Is it country or what? You'd figure if it's green, you're talking about either near a military base. If that's the case, then yeah, then you have a lot of drunk drivers. So looking at this frequency chart, it really doesn't tell us much. Because remember when I asked you, it was up there when I asked you which color has the most frequent, most accidents. We said red because that's what we thought, and we looked. How many of y'all were looking at the screen when you said that? You saw number 41. Right above it is 52. So go ahead and I'll put it on pause. Go ahead and create some of the charts we talked about today. Create the charts for these. Can we do a histogram? Can we do a dot plot? Stem plot? Time series? We can't do that. Why? It's not time series data. It's just one snapshot of it. Can we do a bar chart? Yes. Pareto chart? Yes. Pie chart? Yes. Frequency polygon? Yes. Pictograph? No.
Are we do anything?
Well, we could. Yeah, but how would you represent 23 blue cars? So no, we can't do that either. So from 9, we knocked down to 7. So that's a good start. So let's go back to our data. Here's our data. Here. I want, what chart do I want? Which one we do first? Histogram. What kind is that? Is that a histogram? It's a bar chart because notice they're not touching. Where are all their charts? Histogram, there it is. That's not right. Huh. Our histogram doesn't seem to be working right. Let's do another one. All right. Which ones have y'all done so far? Okay, let's look at Pareto chart. There's with the histogram. Well, kind of. Remember I said earlier about the Pareto chart? So it tells us here which one, because again, so read from left to right, you see the most big one is green, then red, then black, then white. And then remember, I said also that sometimes superimposed with the cumulative frequency chart polygon. So you see that because that tells us that it represents 100% of our data. Ooh, let's look at a pie chart. But that's not what we want. We wanted to tell us more about this. Because what's missing on that pie chart? Yeah, we want to know more about the data. Where is it? Why is it not telling me that? So the fluency for this one is 12%. I want it to be expanded. Here. Chart elements. There you go. Now, if you zoom into this, you'll see the percentage or how much each one takes. There's 52 there, 41, 36, 39, 23. And the legend down here tells you what those represent. Okay, what's the next type of graph you used? Let's look at a frequency polygon. Or a line chart. There. That's a frequency polygon. Does that help us? Not really. What do we know that 1, 2, 3, what are those represent? Yeah, but there's doesn't tell us anywhere. So we have to get a legend. So yeah, so the first element was blue. There are 25 of them. Then it was green, then red, then black, then white, then green or gray. Let's look at a dot plot. Well, we kind of have a dot plot here. If you get rid of these lines, what are you left with? The dots, which are dot plots. So let's look at those again. There's a dot plot. If you look at these, if you superimpose them, you get the same picture. And the last one we can do, if I can find a stem leaf. Got a funnel, got box and whiskers. We'll talk about those later on in this course. It doesn't have per se the stem and leaf one. So what would the stem and leaf? Can we do a stem and leaf on that one? Yeah, it wouldn't do us too much good. I'll show you why. Because the stem and leaf one would look like this. Our outcomes are 20s, 30s, so it's 2, 3, 4, and 5. This is the stem, this is the leaf. With a 20, we have a 5, we have a 3 here, and we have a 5. For the 30s, we have a 6 and a 9. That's all it tells us. All that really tells us is that the 20s and 30s doesn't tell us what colors. It just says the 20s and 30s occurs the most. It doesn't tell us anything about it. So we really can't use a stem plot in that one. All right, so those are our